Hi everyone, welcome to co-learning lecture series. We'll officially get started in just a few minutes, so feel free to say hi in the live chat. Okay, greetings and welcome to episode one of the AI co-learning program. I'm your host Bruce. I'm a Berkeley graduate student and the co-founder of Beta, Berkeley Emerging Technology Association. This lecture series is part of our learning initiative, where we bring together top researchers from academia, industry, and applied labs to explore artificial intelligence across all perspectives. And today is our very first session, and we'll be focusing on a fundamental topic, large language model, inference and reasoning. This is meant to be a warm-up and an onboarding session to help you understand the basic mechanics of how LLMs process inputs and generate outputs. So we will be equipped for more advanced topics in future episodes. And also, just a quick announcement, we'll be giving away 10 open router API keys to lucky audience today. During the lecture and the Q&A session, feel free to drop your questions in the chat and please include your email along with your question. If your question is selected and answered by the speaker, you'll be considered one of the winners, and we'll contact all winners by email after the lecture. Let me now welcome today's speaker, Zhijian Zhou. Zhijian is currently pursuing his PhD in computer science at AUS with research spanning both academia and the real-world AI deployment. Hi, Zhijian.
Hello, hi everyone. Yeah, I'm very honored to be able to give the first lecture for this co-learning program. And shall we get started now?
Yeah, the floor is all yours, please.
Yeah. So thank you everyone for coming for this very first introductory lecture of LLM. So today I'll be sharing a little bit about an introduction to the inference part of large language models. This will cover some very fundamental stuff about how LLMs actually work, inference techniques, as well as some of the acceleration techniques for LLMs. And then I will finish up with the very popular topic of reasoning in large language models. So without further ado, let's first talk about some of the very ground up fundamentals of large language models. As you probably all know, language models, aka LLM, is characterized by a large size of parameters, usually more than 1 billion parameters, and operates on the language space. Now, the very first question we want to ask about a model that process language is that what is a language from a model's perspective? As humans, we all know this language is basically like piecing words together and form sentences or paragraphs for us to communicate, right? But what is language for a model? And for a model to understand language, we must chunk language into appropriate units for the model to be able to understand and predict. So how should we split language into pieces for the model to be able to sufficiently and effectively understand? Now, there will be a lot of intuitive ways of splitting the language. For example, we can split it into letters, words, sentences, or even paragraphs. And they come with pros and cons. For example, if we split the language into letters, that is for we chunk the entire language into single letters and feed them into the language and ask the language model to predict letter by letter. It is the most simple intuitively, but the problem is it may not capture the semantic information we want, right? For example, I tell you the first three letters of a word that start with CAT. There will be a lot of potential next letter that come after it, right? It can be cattle, it can be cater, it can be catch, right? It is very difficult to understand the semantic information. On the other hand, the most intuitive way of splitting language for humans is to actually split in the word level. That is actually how most of people think in terms of language, right? We think in words. That is that is of course very easy to capture the semantic meaning. The model is actually very susceptible to this kind of chunking mechanism because human language is very frequently evolving. New words are constantly created. For example, this word like chillax is sort of like a newly created a word that is now very popular. It's probably not seen by the model or even the world like a few years ago. Not to mention that sometimes we will make spelling errors. In these cases, if you just split the language in the word level, it will give the model a very hard time to understand new words. So how should we resolve this problem? The most popular solution now is to actually split the language into subwords. A subwords is basically a collection of both words and the parts of words. You can think of it as containing letters and words and some chunks of words, sometimes even concatenations of words. This way, we can represent almost all kinds of words, being it misspelling or even like new words, without losing that much semantic meaning from the language. Now, while it sounds very good to just split those, to split the language into just subwords, a challenge is it's very difficult to determine the size of the vocabulary because there's a exponentially large possible combinations of all possible subwords, right? How should we determine what subwords to keep and what subwords not to keep? So to address this problem, people usually rely on this technique called the byte pair encoding method that balance the vocabulary size and the semantic richness. So here is how this BPE technique works. First, you split the entire language into the smallest units. For most Roman languages, including English, it's basically just your letters, right? The 26 Roman letters. For other languages, you probably need to employ some tricks, like splitting the words according to their binary encoding. But let's just assume we are splitting those into letters. So the first the first step is to just split things into letters. Then you are going to merge the letters into subwords that appear the most frequently in the language. Whenever you merge letters into subwords, the vocabulary size shrinks, right? So you can have a more whenever you merge, right, the vocabulary size increases because you have not only letters but also subwords, so that you build more you build a larger size of vocabulary, and you have more semantic richness because you now have a larger chunk of letters. And you just keep doing this kind of merging until you have a satisfactory number of subwords that exist in your vocabulary. So here's an example. Let's say we have a language that consists of only five words: hug, pug, pun, bun, and hugs. And we want to construct a vocabulary out of this. So how can we do this? We can basically first, according to the BPE method, split every word into letters. So here I'm splitting hug, pug, pun, bun, and hugs into letters. And then I'm going to merge the letters according to the most frequently appearing pair. So in this case, you can see that the U and G are the most frequently appearing pair in this basic stream of letters. So I'm going to merge the U and G. Now we have H, UG, P, UG, and PUN, BUN, and HUGS. You can see that we have actually more subwords in this vocabulary than before. If we want more, if we want more vocabulary, we can perform this kind of merging one more time. So in this case, we are going to find the next most frequently appearing pair. In this case, it's going to be the U and N. So we're going to merge all the U and N. Now we have HUG, PUG, and PUN, BUN, and HUG. And we can continue to do this until we have a final satisfactory number of tokens in our vocabulary. Up until this time, you can see that we already have a vocabulary of size 6. As you can see at the bottom left, we now have H, UG, P, sorry, this should be UN, and S, right? So that is how BPE works. So these are some of the fundamentals of this entire language modeling part. And with this, we can continue to talk about how LLM perform inference on these constructed vocabulary. So just now we have talked about this BPE, right? We call this process tokenization. The tokenization is basically the process of converting human natural language into subwords or tokens, which the model can understand. So if you are going to, let's say, call an API from an LLM provider, for example, calling a Cloud API or OpenAI API, this is how it works under the hood. So the first, you will provide language input to the API. And in the backend, they will actually turn this language into tokens using their own tokenizer. And with the tokens, the LLM will recursively, or we call it auto-regressively, keeps generating next tokens until a certain condition is met. And now you have not just the input tokens, but a bunch of output tokens. And then you're going to map all the tokens back to subwords that you can understand. That is, then these are mapped back subwords concatenated together is presented to you as the final answer. A caveat is that a language does not just predict one single output token each time. Instead, it predicts a distribution. And what do I mean by that? We all know that at each time, the vocabulary consists of, let's say, a few thousand or even like 10,000 of tokens, right? The model will not give you one specific token that is going to be the next. Instead, the model is going to tell you, hey, I have this probability distribution for you. The first token has a probability of probably 0.3. The second token has a probability of 0.1. The third token has a probability of 0.1, etc., etc. So you don't just receive a single token out of the model. Instead, you actually receive this kind of array representing the probability of each token. So enable for you to be able to actually get the next token, you actually have to select from this distribution. And this selection actually breeds a lot of very interesting techniques in LLM inference. Some of them you have already seen when you if you have tried using some LLM APIs before. Two of the most well-known parameters for configuring this kind of sampling is called the temperature and the top P parameters. The temperature is something that will help you smooth out the probability distribution. The higher, if you have a higher temperature, it's kind of give you a less difference between tokens with high probability and tokens with low probability. So for example, if originally the model will give you probability 0.7 and 0.3 for two tokens, if you increase the temperature, the probability difference probably drop to 0.6 and 0.4. Whereas if you lower the temperature, the difference is going to be more extreme, probably 0.9 and 0.1. So if you have a higher temperature, you're like treating tokens more equally. Whereas if you have lower temperature, you're like treating the dominant tokens more favorably. And there are, sorry, I think the letter somehow misses from the slides. It's probably because of the rendering, but it's, okay, it's okay. So for top P, we're going to sort all the probabilities in descending orders and only select tokens with the highest cumulative probabilities. For top K, we're going to sort all probabilities in descending order and only select the top K tokens with the highest probability. Now, sampling is a very important aspect for LLM inference because it allows for many tricks to be applied for all kinds of interesting purposes. Some of the examples include beam search, guided decoding, and horizontal scaling of LLM reasoning. In this talk, I will talk about two examples, beam search and horizontal scaling. I'll encourage you to search online to do your own research about guided decoding, which is also very important, especially if you want the LLM to produce some structured output. So beam search, just now we talked about how the model only predicts a distribution of output of this output token each time. Usually, we are only going to sample one token out of this output distribution, right? And we just keep sampling at each iteration until we get a whole sequence. In beam search, we actually sample multiple tokens. So you can imagine that each time the model generates a prediction of the next token, we're going to sample multiple from them. If you keep sampling multiple tokens, you have this kind of a tree of all kinds of sequences, right? Now, every time you will keep this kind of a tree where you have multiple possible candidate sequences, and you only take the most possible next tokens among all the candidates. That is, you're going to trim the tree. You're going to trim some branches that you don't like and keep only the best branches. It's kind of like a tree search if you have taken some data structure courses before, whereas you just keep exploring the tree and do some trimming of the branches. Beam search, as compared to the normal sampling approach, has the benefit of usually generating higher quality output as compared to a normal sampling process. Of course, the downside is that you have to sample more, which means more computational demand for the LLM. Okay, the next question is, how do we know LLM needs to stop? And this is actually achieved by also by also via this vocabulary thing. So here is how it works. We will, when training the LM, inject a special token. Usually this is represented by this EOS token. We'll create this artificial token and just inject it into the vocabulary. So this vocabulary is not associated with any subword that exists in the actual natural language, but it's purely artificial. So we just inject this special token in the vocabulary, and we train the LLM. For all the training sentences we feed to the LLM, we will add this EOS token at the end of this of all the training sentences. So during inference, whenever the LLM produce an EOS token, we know that the LLM has realized this is the end of a sentence, and we will just stop generation. In the same vein, we can use special tokens to handle many other very interesting scenarios. One of the most popular is to handle conversations. So now we all know the most common use cases for language model is to just having conversation or having chats with the language model, right? So how does the language model know when is your turn and when is the language model's turn? This is also handled by special token. Take the Quen series of models, for example. We actually use special tokens to wrap different sections of messages. For example, if we have a system message, we're going to wrap it inside this kind of IM system special token. And for user messages, we're going to wrap them in this kind of IM user special token. And for a system message, we're going to wrap them in this kind of IM assistant special token. So by wrapping text in this kind of special tokens, you kind of inject information in the LLM to make it understand which piece of message belong to whom. And there are many other use cases for special tokens to handle a lot of different use cases. For example, BOS is for start of sequence, EOS for stop of sequence, and PAD to let LM just skip a certain token. These are some of the most common usage. For some of the more advanced usage, people have tried to use special tokens to let the LM summarize the previous text. They have also tried to use special tokens to make the LM perform switching between different subtasks. So yeah, this kind of usage of special tokens tell us there are a lot of room for you to maneuver this kind of special tokens for all the things that you want. So that is more or less about the inference part of the LLM. Next, I will take a few minutes to talk about the fast, the acceleration part of LLM inference. So to achieve fast LLM inference, we cannot escape from this very fundamental idea called the KV cache. The KV cache is, I would say, the key of almost like the majority of LLM inference acceleration techniques. But before we delve into those, let's first figure out what this KV cache really is. So in LLM computation, the heaviest part lies in the calculation of the so-called attention mechanism. So the attention mechanism is just a it's just you can think of the attention as just the matrix multiplication between three matrices, Q, K, and V. And when you are passing tokens to the LLM, you cannot escape from these attention calculations. Unfortunately, this attention calculation is super expensive. So we want to somehow cache some of the calculation in this attention mechanism. So so how can we cache this? We can just cache whatever that has been computed previously for this attention. And this cached computation is called the KV cache. Now, the attention weights is so how does this attention work? The attention weights is represented as a 2D matrix, as you can see on the right. It basically represents the interaction between tokens in the sequence you have so far. So you will see that, for example, we have this kind of matrix representing the interaction between the same sentence. A father wanted nothing to do with her, etc., etc., etc. And each element in this matrix represent the interaction between two tokens. For example, the top left element represent the interaction between father and the father, and the second element represent wanted and father, etc., etc. So when we ask the LLM to generate the next token, we have to augment this matrix to compute whatever the interaction between old tokens and the new token is. However, we don't have to recompute whatever interaction exists there between the old tokens, right? So we only have to compute the interaction between the old tokens and the new token. Therefore, whatever values you have already calculated for the existing matrix can be retained, and you only have to compute the augmented part of this matrix. And so this is why KV cache can accelerate your inference. In autoregressive generation, we only have to compute the attention of the new token against the existing tokens. And the previous whatever scores you have computed can be reused. Now, with KV cache, we can save a lot of time to compute them for matrix computation. This computation is actually not very intensive to the GPUs because the bulk of the matrix computation has already been cached. You don't have to recompute them again. Every time you just have computed that very tiny part of the matrix computation. So usually, most of the time wasted for generating tokens in LLM is to wait for it to generate to wait for the next token to be generated before you generate the next. So we say that the autoregressive decoding is in general so-called IO bound, which means the time is not really wasted in having to perform very heavy computation, but it's wasted in having to wait for the next token to appear before you predict the next. In contrast, we have another stage in LLM inference called the pre-filling stage. Pre-filling is when the LLM first receive a bunch of text that is passed in by the user. So let's say you type in a lot of words and you want the LLM to respond to you. You will probably type like a few hundred words and pass them together to the LLM, right? Now, nothing is cached when you first pass in the text, right? So the model will have to first construct the entire matrix from your text to figure out whatever interaction is among your supplied text. So in this case, since there's no KV cache, the model will have to utilize very heavy computation to construct this kind of attention matrix in this case. So this stage is different from the generation stage where it's just predicting one token at a time. In this prefilling stage is parallel processing the entire input text you supply to the model. Thankfully, with GPU, this kind of matrix computation can usually be done in parallel, but certainly it's going to spend a lot of compute, much more than the autoregressive decoding stage. So in contrast to the decoding stage, we usually say this prefilling stage is compute bound. So if we review what we just said about the decoding stage, the decoding stage is so-called I/O bound, whereas the prefilling stage is compute bound. So to give you a better visual representation, I have prepared this kind of a table comparing the two stages. So whenever you ask the LLM to do a prediction for you, it will first undergo this prefilling stage where you figure out your input text. In this stage, all the computation in this stage, a lot of computation is occurring, and it's going to crunch your input data at the same time. And usually this is fast because it can be done in parallel, but it's going to be computation heavy. After it has figured out the whatever interaction there is for your input, it's going to start to generate next tokens. Now in the decoding stage, where you just keep generating next tokens one by one, the computation cost is much smaller because you have already had the KV cache. But you have to wait because you have to wait for tokens to generate one by one. So in this stage, it's I/O bound. And usually, for most companies, they care more about, they don't really care that much about computation in parallel, but they care more about whether how quick your output can be finished. That's why when you usually use those APIs, you'll realize that input tokens cost much less than output tokens. For example, if you're using a cloud API, you'll realize the input tokens is usually just $3 per million tokens, whereas the output tokens can cost up to $15. And I think the major reason is because the output token generation is I/O bound, and it's going to be very costly if the LLM has to wait to generate tokens one by one. That actually is more costly to the company as compared to the prefilling stage, where you can just parallel compute all your tokens all at once. Now, we've just talked about the decoding stage is primarily I/O bound. Now, we naturally ask, is there a way for us to trade compute for I/O during the decoding stage? That is, can we make computation more heavy during the decoding stage but make it faster? The answer is yes, we can actually do this trade-off. So the idea is that during the decoding stage, right, we can ask a much smaller model to very quickly autoregressively predict a number of tokens, let's say 5 or 6 at a time. Because the draft model is small, it can usually draft models very quickly. Then we ask a large model to kind of do a mini prefilling of these 6 tokens to figure out their augmented matrix all at once. So this is so in this way you can probably save some I/O time because you're processing 5 or 6 tokens at a time, and the autoregressive generation of these 5 or 6 tokens rely on a very small draft model, which is also supposed to be fast. So by doing this, you can actually do decoding faster than the standard decoding. But of course, you have to incur more compute in this case. Here I've prepared an illustration for you. So this is the green part. The green part is the tokens that are successfully decoded by the target model. The red part is the rejected token that is drafted by the small model, but unfortunately not successfully decoded. So with this kind of speculative decoding, we can allow the large model to generate multiple tokens at a time. Of course, it's not successful every time. Sometimes it will be chunked here, sometimes it will be chunked here, all the red points. So, but in general, it's still faster than just generating tokens one by one, right? Because by doing this, you can have more tokens generated at each time, like in expectation. And building on this technique, a lot of variations of techniques have been proposed to further accelerate the decoding speed. I'll just give you some reference, and if you are interested, you can search online and know more about them. To just give you a feeling of how quick this kind of speculative decoding can reach. If you look at the figure on the right, the blue one is the standard decoding speed. Usually, you can just generate like 40 tokens a second. If you use speculative decoding with some tricks built on it, you can increase the speed by almost 3 times. So it's a very significant speed up as compared to the normal decoding procedure. So that is the part about LLM inference. Next, I'll start to talk about reasoning, and that is probably one of the hottest topic nowadays. To get started talking about reasoning, I actually do a ChatGPT search on what is actually the reasoning ability. And here are some of the keywords returned by ChatGPT. These include logical, draw inference, making decisions, and adapting. So, so what do I mean by reasoning for LLMs? It means the LLM is not just simply completing the sentence for you, but instead, we expect the LLM to actually perform some of these characteristics. We expect the LLM to be able to think logically. We expect the LLM to be able to draw inference from whatever is known. We of course want the LLM to be able to make decisions on its own and probably adapt thinking when you shift contexts. How do we inculcate reasoning in large language models? I would say text is actually the perfect tool for formulating this kind of reasoning. Why is that so? Because if you think about it, most of the most rigorous reasoning process that humans have ever created are predominantly written in text. And I'm not sure if you have experienced this yourself. When you are thinking in mind, right, it's not as clear as if you write it down on pen and paper. So this also illustrates sometimes a text is probably even better for representing reasoning than your own mental process. And now, speaking of reasoning, there are two systems of thinking. This idea is brought popular by this very famous book, Thinking Fast and Slow. The author categorized thinking into two categories. The first category is the kind of fast, intuitive, effortless kind of reasoning, but that is not complicated at all. It's usually for you to get information, to sense the world, to recognize pattern. And in the AI world, we usually believe this kind of thinking process is easy. For example, for pattern recognition, 10 years ago, we have already had the ResNet that is able to categorize images into categories, right? For information retrieval, 8 years ago, we've already had the BERT model that is able to recognize sentiment and be able to do some very simple machine translation, right? But it's only in these 1 or 2 years, people have been shifting from system 1 to ask the question, can LLM perform system 2 thinking? The system 2 thinking is characterized by deliberate, analytical, and effortful thinking. So this kind of thinking usually requires a lot of tweaks, a lot of decision making, a lot of planning to achieve a very complicated task. And now, how do we make the LLM perform system 2 thinking? I will introduce two kinds of two families of techniques to instill this kind of system 2 thinking in the LLM. They can be achieved without training or with training. Now, first, let's think about it. The LLM actually have an innate ability to perform system 2 thinking. Why is that the case? Because a lot of the times, logical reasoning can be mimicked. This is just like how you look at the reference solutions from your textbook. Let's say you're a middle school student, first time exposed to this thing called like a Maclaurin series. You have completely no idea what it is, but you can just read the textbook and see the sample deduction, and then you can just try to mimic how that thing is done, right? LLMs being pre-trained on enormous corpora have already had an instilled ability to mimic this kind of a logical reasoning written in human text. So what we need to do is to simply try to bring this kind of innate ability out of the LLM. So following that thread of thought, people came up with this idea called the chain of thought that basically help you to elicit this kind of reasoning ability out of the LLM without even having to train it. So how does this work? In standard prompting, we will just ask a question and expect the LLM to answer it, right? But we can actually try to encourage the model to perform some logical thinking by giving some example of logical reasoning to the model. Right. This is like you trying to write a math proof by following a given math proof for a similar question, right? That's the idea of this chain of thought. So by just giving some examples of logical reasoning, the LLM is able to sort of mimic this kind of logical reasoning and give its own logical reasoning that arrives at the correct answer. People later found out that you don't even need to give samples to the LLM. You simply have to demand the LLM to give you the logical reasoning steps. So building on the previous chain of thought idea, people have came up with this kind of zero-shot chain of thought prompting. So they don't even give logical demonstrations to the LLM. Instead, they simply ask the LLM to think step by step by saying, let's think step by step. And they found out that magically, this short sentence is able to encourage the LLM to display this kind of innate ability to think logically. And of course, sometimes you can even encourage the LLM to think step by step by just having this kind of long-lasting conversation with it. I'm sure many of you have tried this before. Like when you are chatting with ChatGPT, you are constantly reminding the ChatGPT to exhibit some certain kind of reasoning, and this is also a demonstration of why LLM can exhibit this kind of reasoning without even training it. Now, just now we talked about that you can elicit the reasoning, the thinking process out of the LLM by just prompting. And for a lot of the use cases in real life, just being able to think is not enough. And when a lot of the models, like this model of MIT, says that it's best that we can think and do something at the same time, right? So there's this self-reinforcing loop of thinking and acting that help you to do things better. So you cannot just purely think. You cannot just purely make decisions. You have to think a while and then make decision and then think a while. So following this thread of thought, people have came up with this idea of like an iteration between action, reasoning, and observation. So thinking alone is not meaningful. It's not that meaningful. It has to be combined with actions and the interaction with the external world. To give you an example, if I want to find who's the wife of the current president of the US, I would expect the LLM to perform an iterative loop of thinking and reasoning. Of thinking and interacting with the external world. For example, I ask who's the wife of the current president of the US. Then the first step of your thinking is probably, oh, I need to first know who is the current president of the US. Then let's say I don't have this knowledge in my internal knowledge base. I'm going to have to search it online or refer it somewhere. So let's say I just do a web search. The web search is going to return you. Now the current president of the US is Donald Trump. Then the agent has this knowledge and is going to perform the second step of the thought. Now I have knowledge that the current president is Donald Trump. I have to search for the wife of Donald Trump, right? Then the agent can perform the second step of the action, that is to find the wife of Donald Trump. Now the web, this external world, the web, can again return the answer to the LLM saying that, okay, the wife of Donald Trump is Melania Trump. Now the agent being told of this can now tell you the answer that the wife of the current president of the US is Melania Trump. So this is a very classic example of interleaving thinking and interaction with the external world. Let's say you don't have the knowledge of who is the president, who is the wife of the president. It's impossible for you to answer the question correctly, right? So you have to rely on external source, but then you have to be able to know how to query the external source, right? You have to be able to ask the correct question. And that is also a very important aspect of reasoning, to make plans and make decisions. There are some other common reasoning processes that people have characterized before, probably in psychology. They are called reflection and self-consistency. I'm sure you have this kind of experience before, where you thought of something and then you kind of trying to reflect whether that thought is reasonable or not, or you generate multiple paths of thought process and try to see whether they agree with each other before you make a very serious decision in the end. So we can make the LLM agent do these kind of things as well. For example, we can make the LLM do reflection on its own. So the trick is to when the LLM generates a thought process, right? when the LLM generate reasoning traits, we're going to ask a body LLM, which can be the LLM itself, or it can be another LLM, to judge whether this thought process is good or not. So now this body LLM is going to give some feedback to this generated reasoning, and the LLM is going to reflect on this feedback, whether to determine whether this feedback it makes sense or not, right? Before it actually give you the final answer. Another technique called self-consistency is even easier. Basically, you just ask the LLM to generate multiple thinking process, and that arrive at different answers, and you find which answers agree with each other the most, and that is most likely the correct one, right? It is quite simple. It's even naive, but it works, right? Now, building on this kind of mechanism, people have also kind of bring this to the next level. Instead of just like having self-consistency, having multiple thoughts that agree with each other, they let the LLM agent search for the correct thought. So instead of just generating multiple and see which one agree with each other, they generate the thought in a tree manner. So I generate a tree of thoughts, and I trim out some of the thoughts that are most unlikely to be the correct answer, and I keep generating more branches of this tree until I arrive at the final correct answer. And yeah, building on this tree of thought, there's also like even more advanced version called the multicolor tree search mechanism. That is similar to the tree of thought mechanism, but it balances search cost and search quality. I will not delve deep into the exact mechanism of this MCTS, except for the fact that it's kind of interesting. So I encourage to look it up on your own. And all the techniques that I've just introduced just now is now currently in use in a lot of the deep research production-ready implementation, including some of the most popular stuff that you can see right now. For example, this Manus on the right, where if you look at the figure, you'll see that the Manus is actually executing a loop of thought and action. So all the text is just a thinking process, and all these things wrapped in the boxes are just the actions, right? So you can see clearly the interaction between thinking and action, and then thinking and action, and then thinking and action, until in the end you receive a final answer from Manus. So just now I've talked about some of the reasoning process without training. Next, I'm going to talk about how you can actually train the LLM to perform reasoning. Of course, we want to. Of course, we can elicit reasoning from LLM because the LLM has an innate ability to reason. But if we want to instill a stronger reasoning process, we need some practice instead of just prompting. The key idea is that LLMs can be trained to think harder. By thinking harder, I mean generally producing a longer thinking process, right? So how can we train the LLM to think harder? People have experimented a few things, and one of the things they found most successful is to simply make the LLM do difficult math problems. So they just let the cope different but difficult math problems, but they don't provide any supervision for the thinking process, but instead just reward it for correct answers and punish it for the wrong answer. And they explicitly asked the LLM to think before generating an answer. And the interesting thing they found out is that as you train the LLM is somehow learning to generate a longer and longer response. So this tells us that the LLM has learned to perform a harder and harder thinking in order to give you a satisfactory answer. And it actually works. When the LLM generates a harder thinking process, it's actually perform better in terms of solving math problems. So the longer logical reasoning trace actually translates into better performance of the LLM, which is not that surprising. This also demonstrates the effectiveness of reasoning. Basically, if you think hard enough, you can do things that simple naive generation cannot perform. Now, building on this idea, people have been thinking, okay, now you can train the thinking process to be longer and longer. Can we now train the LLM to be able to perform the thinking and action loop longer and longer? So they have experimented on this to train LLM to perform web search, and answer a problem. So what they do is that they ask LLM to think, then perform a web search, then think, then perform a web search. Do this kind of loop iteratively. And they train the model based on real world, so that the model will give will be rewarded if it answers a open domain question correctly, and be punished if it doesn't. And as a result, if you just do this, right, you can also kind of train the reasoning ability of the LLM. As you can see at the bottom, that the LLM trained with this process performs much better, like I think at least 15% better than other methods. Okay. Now, you might be wondering, like, why is that by having a longer reasoning trace can the LLM perform better in solving complicated tasks? Of course, as a human, we know that when you think longer, right, you make plans and you perform search, and then you can arrive at the answer, right? But what is the reasoning for in a mathematical sense? Mathematically, how do we explain this behavior that having a longer reasoning trace, the LLM can perform better? If you think about it, it all boils down to the fundamental formula of LLM prediction. That is, given a bunch of tokens you have already, you're going to generate the next token, right? Now, without the reasoning trace, you just have the prompt tokens, which is just like 100 to 200 tokens, and you have to produce the answer, right? These 100 or 200 tokens is probably not enough to shape the output distribution to the correct one. But let's say you have a reasoning process that is of 5,000 or 6,000 tokens. You have a huge bunch of input tokens available for you to generate a good output token, because these huge input tokens can very well shape your output distribution to the optimal. So mathematically, that's why reasoning process makes sense, right? Having a longer reasoning process usually means your output distribution is more likely to be the correct one. With this discovery, people have been very excited because this kind of reasoning reveals a trade-off between time and space. In the past, right, people have been focused on parameter scaling. Basically, by building a larger and larger model, you can have better and better performance. That's why people have been building like models of 1,000 billion parameters and even more. But then people quickly realized that there's diminishing return, right? In order to perform, in order to make the model perform like 10% better, you probably have to double your parameter size, or even more. But currently, I think 1,000 billion parameter is probably the limit of human resources capacity, right? It's very difficult to train an even larger model. Now, it seems that we have already reached the peak of this current scaling law. How can we further boost the model performance? Here, this idea called inference time scaling comes to the rescue. They're basically telling you, hey, you don't have to scale up the model parameter size anymore. Instead, you just make the model think longer. So the longer the model can think, the better it performs as well. So there are two directions you can optimize your performance. One is to build a larger model. Another is to make the model think longer. So they exist in orthogonal directions. That is what makes people exciting, because they don't interfere with each other. Of course, if you pursue this kind of inference time scaling to the extreme, it's not that ideal, because there is a context limit to your model, right? In the past, I think in 2023 or 2024, most models can only handle around 10K context size. And nowadays, a lot of the companies claim their models can handle like 1 million tokens, but most of them are not meaningful, right? So your effective context window is usually just around 10 to 20K tokens. Beyond that limit, your model performance will degrade drastically. So inference time scaling is not as good as you might think. Well, within a very short context window, like let's say 10K tokens, it can scale. It can scale very well. But beyond that point, there will be problems. Especially if you see from this figure, this manners interaction, the manners literally tells you that the context has too many tokens and it is affecting its performance, right? That also reveals how this kind of context management is a key challenge to inference time scaling. So how can we address this kind of inference time scaling problem? There are quite a number of ways that I am going to introduce you with the remaining time. The easiest is not the easiest. The most popular approach is to break a large task into subtasks and assign them to sub-agents. And after each agent finish the subtask, you only consolidate the answer and discard the context for that subtask. So by doing that, you can save some of the context. But then this is very tedious in terms of engineering. It requires a lot of fiddling of your AI agent system, and it doesn't really provide a satisfactory performance in most cases, right? The second approach is a trained approach. Basically, you can train the LLM just like how you train it for reasoning process. You can train the LLM to dynamically compress its memory when it is generating new tokens, when it's generating its reasoning process. And this way, you don't have to really handcraft your memory management, your context management. You can just train it to do this. But this direction is still under exploration, and it has not matured into a production-ready paradigm. So there's still a lot of research that needs to be done. So here, with this, I'm sure you have already seen the trade-off in this kind of inference time scaling. When you want to achieve effectiveness, you also want to achieve efficiency, right? When the models can improve problem solving with reasoning, we also have to be aware not to make these reasoning traits too messy and redundant, such that it crams your context window. So another line of work that help you to address this is to make your reasoning process more clean, right? It's not just like a chunking your memory or discarding unnecessary, but rather like when you are generating the reasoning process, generate it in an efficient way. So let's say you are solving a math problem. If you can use a formula, don't deduce the formula first. Something like that. So how do we encourage the model to not do overthinking, to think efficiently? There are a few ways. The most naive way is to just prompt the model, say that, hey, you can perform logical reasoning, but don't do it for more than 100 words. That sometimes work, but most of the time it doesn't work, because the model is very notoriously not really following word restrictions. Another way is to force the model to stop generation after a certain number of tokens. This is actually the most practical approach, and you actually can find a lot of the large companies using this in its reasoning process. For example, I'm not sure if you have tried O3. O3 is somehow employing this strategy in its reasoning process. You'll often see words cut off at a certain point in its reasoning process. This is probably one of the ways it used to curb the overthinking under the hood. And other ways you can use to curb overthinking include gathering high-quality reasoning traits to fine-tune the model, right? So it's like asking a teacher to teach you the most efficient way of thinking about a problem so that you don't go to all kinds of sidetracks, right? And also, you can also train the model in a reward manner, basically rewarding the model if it generates a shorter trace and penalizing the model if it generates a longer trace, right? Now, in real life, you can also use an API to curb overthinking. For example, if you're using Cloud API, you can actually determine how hard you want to think by giving it a budget token number in the API. So this will limit the amount of reasoning the LLM performs, right? So if you want the model to, let's say you think this problem is hard and you want the model to think very hard, you can probably give it a higher number of budget tokens and vice versa, right? Okay, then I think I will end my session here. I'm opening the floor for question and answers. Thank you.
Thank you for the fantastic talk, Zian. Now we're open to the floor to questions, so feel free to drop the questions in the live chat. Okay, so the first question we have here is about BPE, byte pair encoding. That's why is BPE so important in so many contemporary large language models, and what are the significant advantages of BPE compared to other tokenization methods, such as word piecewise and unique graph? Yeah, that's the question.
Okay, let me just go back to that slide. I guess one of the key advantage of BPE is that it's actually very easy to implement. If you think about it, there is no human involvement in using the BPE method. You don't have to do anything. You just have to throw in a bunch of text to the BPE trainer, and then just let it merge and merge and merge. And another advantage is that you can actually tell the BPE what is your preferred vocabulary size. For example, in 2023, most of the language models have a vocabulary size of around 10K. Now it's crazy. Now, let's say, I think the newest Quant model has already reached to 10K in the vocabulary size. Of course, in this case, you need you need different kinds of of tokenization, right? And with BPE, you can just tell the BPE what is your ideal vocabulary set, and it can construct this kind of vocabulary for you automatically. I think that's the beauty of this technique. And you can, it's not hard to imagine that in the future, maybe 2 years ahead, we are going to require an even larger vocabulary, maybe like 50K or even 100K, or like maybe even a million K in terms of vocabulary for your tokenization. I think Bruce is disconnected.
Hi again.
Are you just disconnected?
Yeah, sorry.
Okay. No
Now
problem.
we have the second question here. What are some of the most effective inference frameworks currently available, and what underlying techniques or architectures do they utilize?
Some of the most popular inference frameworks, I would say, if you're talking about open source ones, they are just the most most popular should be VLM and SGLang. I personally have only tried VLM because VLM is more suitable for doing research, whereas SGLang is usually more towards production-ready deployment. So depending on your use case, you may use either of the two.
Okay, thank you. The next question is, how do top P and the top K sampling differ in their control over low probability token choices?
Okay. Usually, okay, mathematically, there is always a way to make them equivalent, because essentially they're just like sampling the top tokens. So you will realize nowadays a lot of the API providers only offer one of the two. Usually they offer top P nowadays. If you check out the OpenAI API website, I'm sure you can see that there's only a top P available. This is because essentially they are mathematically equivalent if you configure them appropriately.
Okay, thank you. Can you discuss the benefits of using CPU-only models like BitNet for specific use cases and suggest where GPU is not necessary?
Oh, I'm not really very familiar with CPU-only language models because I think I've made very clear in the slides that we are talking about language models with parameter size more than 1 billion. So it's
Yeah,
probably difficult.
that may be something we can discuss in the future.
Yeah,
Uh,
definitely.
okay. Next question is, how does the tree of thought framework extend beam search to structured exploration of reasoning paths?
Okay. So I think they share some similarities, but they are not entirely the same. Essentially, for beam search, right, it's a token for you to do sampling. So you can think of the granularity as token level. So for beam search, every time you are just sampling multiple tokens from a token distribution. Whereas for tree of thought, right, it's more of like a reasoning block level. So for tree of thought, you're going to sample from a bunch of tokens. You can think of it that way. Where's my tree of thought? Okay, so here, these boxes are not just tokens. They are actually a bunch of tokens that represent a piece of thought. So, so for tree of thought, you're actually exploring in the thought space. You are not exploring in the token space. So that is the key difference. Yeah, but I would acknowledge that for both beam search and tree of thought, right, they have the ability to provide you with a better output than the original sampling output.
Okay, great. The next question is there a limit where context growth starts negatively impact reasoning quality?
Sorry, could you repeat the question? I
Yeah.
didn't really get it.
Is there a limit where context growth starts negatively impact reasoning quality?
Yes, there definitely is. If you can just do it, you can just do an experiment on your own. Just make the LLM keep generating the reasoning trace. Uh, as for how to do it, you can search online. There are a lot of ways to help you just like manually make the LLM think longer and longer, and you will see that uh, like extending over a certain point, maybe like I think 20K or 30K, depending on your model size, the performance actually starts to drop.
Mm-hmm.
Yeah. So there is a limit, like empirically.
Okay, thank you. I think that's pretty much all the questions for Q&A session. Thank you, guys.
Yeah.
So
Thank you.
let's wrap up with a quick summary. Today we explored how LLMs process input and generate output, what inference looks like under the hood, and how reasoning can be achieved through prompting and fine-tuning. So if this was your first time joining, welcome to the co-learning community again. And don't forget to scan the QR code to join our Discord and Telegram. Please follow Spoon OS and please subscribe this channel for future lectures. Big thanks again to Zijian and to all of you for being part of this. In the next episode, we will talk about reinforcement learning. So see you next week. Bye.
Yeah. Thank you, everyone. See you.
Thank you.
OK，结束了，然后我们已经按着 live 了，谢谢老师，
谢谢。
谢谢。
那个